Lumen point. Let's begin the breakdown.
So there's this one simple rule in mathematics that feels like it just has to be true. But here's the catch. If you accept it, you can take a solid sphere, break it into just a few pieces, and then put them back together to make two identical spheres. Today, we're going to dive into the wild story of the rule that makes this all possible, the axiom of choice. Okay, seriously, let's wrap our heads around this. Imagine you're holding a solid gold ball. You break it apart into 5 pieces, you move them around a little bit, and then you reassemble them. And suddenly, bam, you are now holding two gold balls. Each one is a perfect identical copy of the original. No extra gold, no tricks. This sounds completely impossible, right? But it's a real mathematical theorem called the Banach-Tarski Paradox. And the secret behind this whole magic trick? It all comes down to one of the most controversial, most fought-over ideas in the entire history of math. It's an axiom that makes us question everything we think we know about infinity and even the simple act of choosing. So where does this all start? Well, it begins with a problem that seems pretty simple on the surface. See, in math, you can't just pick something. You need a rule. If I asked you to choose the smallest positive whole number, you'd say 1, no problem. But what if I asked you to choose the smallest real number that's bigger than 1? Including all the decimals. Is it 1.1, 1.01, 1.00001? You can't. You can always find a smaller one. That is the problem of choice with infinite sets, and one man made it his life's mission to solve it. For the longest time, brilliant minds like Galileo basically thought all infinities were the same size. He reasoned that since you can match every whole number to a perfect square, the set of all numbers and the set of all square numbers must be the same size, even though one seems smaller. But then, in 1874, a German mathematician named George Cantor came along, and he just wasn't buying it. He had a gut feeling that some infinities were way, way bigger than others. And he proved it with this absolutely ingenious trick, the diagonalization proof. He said, okay, just imagine you could do the impossible. Imagine you have a complete list of every single real number, numbered 1, 2, 3, and so on. Then he showed how to build a new real number that by definition could not be on that list. He did it by taking the first decimal digit of the first number, the second digit of the second number, and so on, right down the diagonal. He changed every one of those digits to create his new number, and because of how he made it, it was guaranteed to be different from every single number on the supposedly complete list, which meant the list was never complete in the first place. And just like that, Cantor had proven that infinity comes in different flavors. You've got your countable infinities, like the whole numbers that you can kind of line up one by one forever. And then you have uncountable infinities, like the real numbers, which are just fundamentally provably bigger, a whole new level of infinity. This discovery completely rocked the mathematical world. But Cantor, he wasn't done. Oh no, not by a long shot. He had an even bigger, bolder goal: to prove that any set, no matter how huge or messy it was, could be put into a perfect, definitive order, what he called a well order, where every part of it has a definite starting point. He was utterly convinced that even the chaos of the uncountable real numbers could be lined up neatly, first, second, third, and so on. He called it his well-ordering theorem. He just knew it had to be true. But there was this one massive problem. He couldn't prove it. And you have to understand, for Cantor, this conviction wasn't just mathematical, it was deeply spiritual. He was a devoutly religious man, and he truly believed that his incredible insights into infinity were basically divine revelations. To him, this wasn't just some theory, it was a glimpse into the mind of God. But the mathematical establishment, they were horrified. And leading the charge against him was his very own former teacher, Leopold Kronecker. He saw Cantor's work as a sickness, a grave disease infecting mathematics. He attacked him in public, relentlessly, calling him a charlatan who was corrupting the next generation of mathematicians. The pressure was just immense. Cantor's dream job at the University of Berlin kept getting shot down for mysterious reasons. The constant, vicious attacks from the man who was once his mentor took a devastating toll. In 1884, he suffered a severe nervous breakdown and had to be sent to a sanitarium. Unable to prove his theorem, rejected by his peers, George Cantor, the man who stared into infinity, eventually just retreated. He walked away from mathematics, a broken man. So for years, Cantor's unproven theorem just sort of haunted mathematics, But then, in 1904, a mathematician named Ernst Zermelo came along. He was fascinated by Cantor's ideas, and he was pretty sure he'd found the missing key. Zermelo had this light bulb moment. He realized that Cantor, and actually a lot of other mathematicians, had been making this huge unspoken assumption the whole time. They were just acting as if they could make an infinite number of choices all at once, even when there was no rule telling them which things to pick. So Zermelo decided to make it official. He wrote it down and called it the Axiom of Choice. Now, the axiom doesn't tell you how to choose or which element to pick. It just says you can. It asserts that a set made up of one choice from each of an infinite number of other sets can exist. And with this one little axiom, Zermelo proved Cantor's well-ordering theorem in just 3 pages. He had finally unlocked it. So, Cantor was finally vindicated. Huge win, right? Well, yes and no. Because mathematicians very quickly discovered that when you open the door for the axiom of choice, some really, really weird stuff comes through with it. The axiom, it turned out, had a dark side. One of the first freaky results was something called the Vitali set. Using the axiom of choice, a mathematician created a set of points on a line that you just can't measure. It's not that its length is 0 or infinity. It's that the question, how long is it, makes no sense. It's like asking what the color of a musical note is. This totally shattered the common sense idea that any group of points has to have a measurable size. But that was just the opening act. Because in 1924, Stefan Banach and Alfred Tarski used the axiom to prove something that feels less like mathematics and more like actual sorcery. They proved that you could take a solid sphere and, using the axiom of choice, break it down into 5 special, infinitely complicated sets of points. These aren't pieces you could cut with a knife. They're more like infinitely fine dust clouds, so strange they have no defined volume, just like that Vitali set had no defined length. Then all you have to do is rotate and move these weird pieces. So, picture it. You start with one solid sphere, totally normal, fixed size, fixed volume. You take these bizarre, undrawable sets of points, and you just move them. You rotate them in space, no shrinking, no stretching, no tricks. And you end up with 2 perfect spheres. Each one is absolutely 100% identical in volume, density, and size to the one you started with. No extra matter added. This is the Banach-Tarski Paradox. It's a logically flawless consequence of accepting the axiom of choice. So this created a full-blown crisis. What do you do with that? Mathematicians were totally torn. On one hand, the axiom was incredibly powerful, helping to prove all sorts of useful, important things. But on the other, it led to these absurdities that just seemed to violate all common sense. So what is it? Is the axiom true, or is it false? And the answer, when it finally came from the work of Kurt Gödel and Paul Cohen, was maybe the weirdest part of the whole story. It's neither. The axiom of choice is independent of all the other rules of math. You can't prove it's true, and you can't prove it's false. It's just like the famous parallel postulate in geometry. You can choose to accept it, and you get the flat geometry we all learn in school, or you can reject it, and you get weird, curved geometries. Both are perfectly logical. It's the same with the axiom of choice. You can choose to live in a mathematical universe with it in all its paradoxes, or you can choose to live in one without it. Today, most mathematicians do choose to accept the axiom of choice because it's just too useful to throw away. But this whole crazy story leaves us with this huge, profound question that cuts to the very heart of what math even is. Are we uncovering these timeless, objective truths about how the universe works, or are we actually just building different logical universes based on the fundamental choices we decide to make?
Fuel your curiosity. Subscribe for the explanation. Stay for the knowledge.